Okay, this is the first video of 3 videos on section 7.4 looking at area and arc length in the polar coordinate system. So area of a polar region, the area of a sector of a circle, so let's go ahead and draw a circle and sector like a slice of the pizza of radius r, and that's going to be a central angle, which means the angle is formed with the vertex as the center of the circle. And this is going to be in radians. Okay, so the area of that sector there is going to be 1/2 theta r squared, where theta is in radians. Suppose r equals f of theta is a continuous and non-negative on the interval where, well, I have the inequality, but theta is between alpha and beta, and where beta minus alpha does not exceed 2 pi, or a full 360 degrees. So a little bit of the idea here is our curve, r equals f of theta, and then we're going to have our radial lines there. So it says the area of the region bounded by the graph r equals f of theta between radial lines theta equals alpha and theta equals beta. Okay, is, and so there's that formula here. So let's try to motivate that a little bit. Okay, so we're going to form a partition, and so alpha would be our theta naught, and then we have a theta 1, and then a theta 2, and a theta 3, etc., all the way out to beta, which would be our theta n, which I think we'll label in a minute here. So we're going to partition the interval alpha to beta into n subintervals. Alpha equals not theta 1, theta naught, sorry about that. We got our numbering system off here. Okay. Theta 1, theta naught, theta 1, all the way out to theta n, which will be beta. Yep. Okay. The delta theta will be beta minus alpha over n, so we're going to use a uniform partition. So the area is going to be approximately, so we can think of all of these as little sectors. Okay, so a bunch of area of sectors, and we're going to sum them up. So we're going to sum up the first one to the nth one, and that's going to be 1/2, and then it's going to be r squared, and we're going to use f of theta of delta I. So that's going to tell us how far away we are from the pole. Square it, and then delta theta. And then if we let the norm of our partition go to 0, then we'll end up with the integral. And we have, we have the integral, so we have the area is equal to 1/2 the integral from alpha to beta, f of theta squared d theta, or we can write that as 1/2 integral from alpha to beta r squared d theta. And so we're going to work on 2 or 3 examples here in finding the area of some sort of polar graph. Okay. So first example here, we're going to find the area of the region bounded by the graph r equals 4 cosine of 3 theta. And I believe we graphed this exact graph or something very, very similar to it in the previous section 7.3 videos, one of those. I want to rig things nicely so that I have the nice 0, pi over 2, pi, 3 pi over 2, and 2 pi for graphing this. So the argument here is 3 theta. So we want 3 theta to equal 0, pi over 2, pi, 3 pi over 2, and 2 pi. If we divide all of those by 3, then theta will be equal to 0, pi over 6, pi over 3, pi over 2, and 2 pi over 3. And we're increasing by pi over 2. So we have theta is equal to 4 cosine of 3 theta. When we evaluate this at 0, we're going to get the cosine will be 1, so 1 times 4 is 4. When we evaluate at pi over 6, the argument will be pi over 2, and cosine of pi over 2 is 0. Evaluated at pi over 3, that will give us the cosine of pi, which is -1 times 4 is -4. evaluate pi over 2, and we get 3 pi over 2 inside the cosine, which will be 0. Okay, and then lastly, at 2 pi over 3, that'll give us the cosine of 2 pi, which is 1 times 4 is 4. Okay, so we're going to go ahead and graph this in 2 dimensions. Okay, so we have our first maximum at 4, 0. So let's go ahead and plot 4, 0. And then we have pi over 6, and then also negative pi over 6. We're going to use a little bit of symmetry here. This is the cosine graph, which is going to be symmetric with the y-axis. Okay. And so we'll use the radial lines pi over 6 and negative pi over 6 to kind of guide this. This is a rose curve. It's going to have 3 petals. Okay. And then we'll continue on with the next rose petal. So it's going to have its minimum here at pi over 3. Okay. So because it's going to be a negative 4, we're going to go on the opposite direction of pi over 3, which is going to connect to 4 pi over 3. Okay. So remember, you go the opposite direction. So instead of going to 4 this way, we'd go in the opposite direction. And pi over 6 and pi over 2 is where this is equal to 0. And so we'll use those radial lines to help graph this. Okay. All right, now we're ready to do our last petal. So we have 2 pi over 3 is where it's going to hit its maximum. Remember, we're increasing by pi over 6. So that's 4 pi over 6 plus pi over 6 would be 5 pi over 6. Okay. And so at 2 pi over 3, we're going to go out to 4. And then we'll use the radial lines 5 pi over 6 and pi over 2 to kind of help us guide the graph there. Okay. All right. And so there's our rose curve. And we want to find the area of this rose curve here, the region that's bounded by it. Now, by symmetry, all 3 of those petals are going to be the same. And so our area formula, the 3 is for the 3 petals, and then it's 1/2. And then I can use any of the petals there from negative pi over 6 to pi over 6, from pi over 6 to pi over 2, or from pi over 2 to 5 pi over 6. Any one of those will work. You'll get the same area. I'm going to go ahead and use the first one, which is negative pi over 6 to pi over 6. And then it's going to be our function, r, which is 4 cosine of 3 theta squared. And then d theta. Okay, so it's going to give us 3 halves. Integral from negative pi over 6 to pi over 6. 16 cosine squared of 3 theta, d theta. We're going to go ahead and use a power reducing formula. Cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. Notice that your angle gets doubled, so the cosine of 3 theta, that will be doubled to a cosine of 6 theta. All right, so 3 halves times 16, and then times 1/2, and we use the power reducing formula, is going to give us 12. So we have 12 integral from negative pi over 6 to pi over 6 of 1 plus cosine of 6 theta d theta. Again, I went ahead and took care of the 1/2, so you see that 1/2 there. That is from the power reducing formula. All right, now we're ready to integrate it. So this is going to be 12 theta plus the sine of 6 theta divided by 6, and then we're going to evaluate that from negative pi over 6 to pi over 6. So it's going to be equal to 12 pi over 6 plus the sine of 6 times pi over 6 over 6. We've got a syntax error. Fix it. Okay, minus the quantity, negative pi over 6, plus sine of 6 times negative pi over 6, all over 6. Okay, so this is going to be 12 times pi over 6, and then sine of 6 times pi over 6 is just going to become the sine of pi, which is 0. And then we got minus negative pi over 6, which becomes positive pi over 6. And then we're going to have minus sine of 6 times negative pi over 6, which becomes the sine of negative pi. And that's going to be 0, so whether you want to say minus 0 plus 0 doesn't matter. Okay, so that gives us 12 times pi over 6 plus pi over 6 is 2 pi over 6, which reduces to pi over 3, times 12 will give us the area of those 3 rose petals altogether is going to be 4 pi. Okay? All right, I think I got 2 more examples here of finding the area. So let's go and look at the next one. So we're going to look at r equals 2 cosine of 2 theta. This is also a rose curve. The argument here is 2, so it's an even, so we're going to double that, so there's going to be 4 petals on this. I want to have the nice values on the unit circle being 0, pi over 2, pi, 3 pi over 2, and 2 pi. So what I want is I want the 2 theta to be equal to that. So 2 theta is equal to 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm going to divide each one of those by 2, so we have 0 pi over 4, 3 pi over 4, hold on, I got off here. 0 pi over 4, excuse me, pi over 2, then 3 pi over 4, and pi. And so we'll make our little table here. 0 pi over 4, pi over 2, 3 pi over 4, and pi. And then this is just going to follow the cosine pattern here. However, let's see. However, I seem to have 4 on the brains because of the previous problem. So let's go ahead and, just for convenience, let's go ahead and change this to 4 cosine of 2 theta. How it's going to work is going to be similar if it was 2 cosine of 2 theta. So we're going to have it as 4. Okay, and then cosine of each. We can go ahead and evaluate each one of these individually, and we can come up with this table here. Let's go ahead and look at the graph. Okay, so we're going to have our maximum at 4 and a minimum at negative 4, and we're going to be increasing by pi over 4. Okay, so I have my first point plotted there at 4, 0, and then at pi over 4, we're going to be at 0. To complete this petal, we're going to dial it back to negative pi over 4. Okay, and there's one petal there. We can put in our radial lines of pi over 4 and negative pi over 4, and that'll help us with the sketch of the petal there. Okay, so let's go on and label the orientation there, and then we'll do the next petal. So at pi over 2, we're going to be at a minimum. Okay, and then our zeros are going to be at pi over 4 and 3 pi over 4. So at pi over 2, we're going to go the opposite direction, and so instead of going up to 4, we're going to go down to 4 the opposite direction because it is a negative 4 directional distance. Okay, and then we'll use our radial lines, pi over 4 and 3 pi over 4 to help guide our graph here. Okay, so there is our second rose petal. Alright, if we want to do another one, the maximum is going to occur at pi. We're increasing by pi over 4, so the next one would be 5 pi over 4. Okay, so that's going to be a positive 4, so we're going to have 4 comma pi, and then we're going to use the radial lines of 3 pi over 4 and 5 pi over 4 to kind of help guide the rose petal. Alright, and we got one more to go, so we're going to increase by 5 pi over 4 and get 6 pi over 4. Which is 3 pi over 2. We're going to have a minimum again. And 6 pi over 4 plus pi over 4 is not going to be 5 pi over 4. That's going to be 7 pi over 4. Okay, 7 pi over 4. All right. And that's going to help us get that last rose petal in there. Okay. All right, now think of it as practice of doing the sketch and then also in finding the area. We're going to find the area, and then by symmetry, we only need to find the area of one of them, and then multiply that by 4. So you could find it from negative pi over 4 to pi over 4, or from pi over 4 from 3 pi over 4, or from 3 pi over 4 to 5 pi over 4, 5 pi over 4 to 7 pi over 4. Any of those would work. I'm probably going to use the first one there. So the area is going to be 4 for the 4 petals times 1/2. integral from negative pi over 4 to pi over 4 of, oh, I see. Okay, I went ahead and fixed that. Okay, so I had 4 on my brain again. All right. So the r squared is 4 cosine of 2 theta quantity squared. So let's go ahead and simplify that. So on the outside, we're going to have 2 integral from negative pi over 4 to pi over 4 of 16 cosine squared of 2 theta d theta. Okay. Power reducing formula, cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. Which means we have the existing 2 on the outside times 16, and then we're going to get a 1/2 from the power reducing formula. And so that's going to give us 16 on the outside there. So we have 16 integral from negative pi over 4 to pi over 4 of 1 plus the cosine of, double your angle, 4 theta d theta. So it's going to be 16 theta plus the sine of 4 theta all over 4, and that's going to be evaluated from negative pi over 4 to pi over 4. So we have 16 times pi over 4 plus the sine of 4 times pi over 4 over 4 minus the quantity negative pi over 4 plus the sine of 4 times negative pi over 4, and then that's divided by 4. So it's going to be 16 times pi over 4. Sine of pi is 0. Minus negative pi over 4 becomes positive pi over 4. The sine of negative pi is 0. And so we have 16 times pi over 4 plus pi over 4 is 2 pi over 4, or pi over 2. And so the area of the 4 rose petals there together is going to be 8 pi. Okay. This one's going to be a little bit longer. I got one more here for you. So we're going to find the area inside the circle r equals 15 sine theta, and outside the cardioid 5 plus 5 sine of theta. So there's no multiplier inside with the theta, so we'll just use 0, pi over 2, pi, 3 pi over 2, and 2 pi for our table. All right. And then we'll go ahead and graph this 5, 10, 15, negative 5, negative 10, and negative 15. Let's label all that stuff. Okay. So the 15 sine of 0 is 0. 15 sine of pi over 2 is 15. At pi is 0. At 3 pi over 2 is negative 15. And at 2 pi is 0. So we'll go by 5s here on our rings. So at pi over 2, we're going to have our maximum. And this is going to be a circle. Once we get into below the x-axis, we're going to have a repetition. So we would be retracing the whole circle. And then once we get up here to pi over 2, actually it would be 3 pi over 2 and negative 15, but that's going to send us in the opposite direction. And then when we're over here, that's going to sketch the rest of the graph here. Okay. All right, now let's go ahead and look at the 5 plus 5 sine of theta. That's going to go 5, 10, 5, 0, and 5. Okay. So we're going to start out at 5, 0, and then we're going to go to pi over I guess would be 10 and pi over 2. Okay. And then we're going to go to 3 pi over 2. We're going to go to pi and 5. And then at 3 pi over 2, we'll have the point 0 and 3 pi over 2. So we'll have a little bit of a dimple there. Or mine looks kind of like an upside down heart, I suppose, the blue graph there. Okay, so we want to find the area inside the circle but outside the cardioid. So we do have our radial lines roughly there. I've shaded in that area we want to find. So we need to find where these polar graphs actually intersect. So where does the 15 sine theta Where is that equal to 5 plus 5 sine of theta? Well, subtract 5 sine of theta from both sides, and then divide by 10. We have the sine of theta is equal to 1/2. That's going to occur at pi over 6 and 5 pi over 6. And so I'm going to just redraw that a little bit. And so those are your radial lines there. Okay. Now for the area is going to be 1/2. And then we're going to do the integral from pi over 6 to 5 pi over 6. Another possibility, because of the symmetry, you could do 2 times the integral, 1/2 the integral from pi over 6 to pi over 2. And so you'd split it up into 1/2 and 1/2, and so you double that. So you can do that also. I'm just going to do the whole thing. So 1/2 integral from pi over 6 to 5 pi over 6. And you have your outer function, 15 sine of theta, minus your inner function, and each one of those respectively r squared. Okay. Alrighty, so we're going to have to expand that out. So we're going to have 225 sine squared minus 25 minus 50 sine of theta and minus 25 sine squared theta d theta. Collect our like terms. We have 1/2 integral from pi over 6 to 5 pi over 6 of 200 sine squared of theta minus 50 sine of theta and minus 25 d theta. Okay. We're going to finish up this computation on the next slide. So there's what we had just a moment ago. So this is equal to 1/2 integral from pi over 6 to 5 pi over 6. And we're going to use our power reducing formula. Sine squared of theta can be rewritten as 1/2 1 minus the cosine of 2 theta. So 200 times 1/2, 1 minus the cosine of 2 theta, minus 50 sine of theta, and minus 25. So it's going to be 1/2 integral from pi over 6 to 5 pi over 6. And let's see what we got. We got 100 minus 100 cosine of 2 theta. And then we have the minus 25, so that makes the 75 minus 100 cosine of 2 theta. And then minus 50 sine of theta d theta. So we'll go ahead and integrate. So 1/2 times 75 theta minus 100 sine of 2 theta divided by 2 plus 50 cosine of theta. And we're going to evaluate that from pi over 6 to 5 pi over 6. So 1/2 75 times 5 pi over 6 minus 50 times the sine of 2 times 5 pi over 6 plus 50 cosine of 5 pi over 6 minus the quantity 75 times pi over 6 minus 50 sine of 2 times pi over 6 and plus 50 times the cosine of pi over 6. Okay, which is equal to 1/2. And that's going to give us, let's see, 125 pi over 6. Sorry, over 2 now. The 6 goes into the 75 25 times, and then times 5 would be 125. Okay. I don't think we're going to combine these just yet, so let's not underline those yet. Okay. Minus 50, and then we have the sine of 5 pi over 3, which is going to be negative root 3 over 2, plus 50 cosine of 5 pi over 6, which is going to be negative root 3 over 2, minus 25 pi over 2, plus 50 times the sine of pi over 3 is root 3 over 2, plus 50, minus 50, and the cosine of pi over 6 is going to be root 3 over 2. Okay, so we have positive 50 root 3 over 2 and a negative root 50 over 2. If I can say that. Negative 50 root 3 over 2. And then we got a positive 50 root 3 over 2, and a negative 50 root 3 over 2. Those are all going to absorb. 125 minus 25 is going to be 100. So we have 1 half, 100 pi over 2. And when that's all said and done, that's going to reduce down to 25 pi. And that's going to be the area inside the circle and outside the cardioid. Okay. Well, stay tuned. We got 2 more videos from this section.